we're going to start the section of the class that deals with OpAmps. OpAmps are different than something you've dealt with before. They're actually super simple, but nobody ever thinks they are. So,
circuit diagram doesn't look extreme.
no, it doesn't. It's made up of a whole bunch of stuff. And you don't know probably at this point what any of those things, well, some of the things you do. First of all, there's 20 transistors inside each one. We haven't learned about transistors, but that's actually the basis. Those are all little transistor amplifiers, which we will actually study later, but not nearly in as complex a fashion. There's also 11 resistors. Resistors you know about, so that's good. And one capacitor down in there. But it's all made on a chip. So you will actually just get that. The op-amp itself, and the one that you will have, you probably already do have in your lab kit, is actually a bit more delicate than other things, so be careful with it, because it's really, really easy to make them not work, given all that stuff inside it. But basically, there are 8 pins, for which 2 of them are, actually 1, 2, 3 of them we never use. We never use 1, 8, and 5. Never use those in here. And the plus V and the minus V are actually for power supply, because they have to be powered. So if you do not have DC power connected to them, they won't work at all. They require that in order to get the system inside to be a certain DC voltage so that the signals can be processed. So when you get to the point where you're doing the lab, the first thing you're going to do is connect power to the op-amp, and then you're going to leave it and never disconnect it until you build the circuit again. But we will talk about all that later. We're not quite to that point yet. So op-amps are a wonderful kind of amplifier for many reasons. They don't cost a lot. They're super cheap, actually. And they have actually, depending on which op-amp you use, they have a really wide variety of characteristics. The gain of an amplifier can be totally different depending on what kind you're using, but that's just the ratio, again, of the output to the input voltage. So depending on the type of op-amp you're using, the gain can vary significantly. They can have different input and output impedances, which, as you know from studying amplifier characterization, is important. So some of them have, depending on the type, different input and output resistances. They have different bandwidths depending on what kind of signal frequency you use. And in this class, we don't spend a lot of time talking about frequency characteristics. So you're pretty much going to be able to assume that whatever frequency you're using will work. And they also differ as far as power consumption, how much power they use and how much power they can process. So given that, you can use operational amplifiers for many, many, many things. You can make a fixed gain amplifier, you can make a variable gain amplifier, and they're actually super, super easy when we get to that point to make. We won't do that this week, but next week we will, and you'll see it's not difficult. You can make filters out of them. You can make what are called active filters, which work in a similar fashion, but there's actually many, many, many more types of filters you can make with an op-amp. There's a whole, in fact, up in my office, I have a whole book on analog filters made with op-amps. It was a whole course I took. So it's like this thick, and it has different circuits you can make with op-amps to make filters. So there's a lot you can do with that. You can make integrators and differentiators. You can make a signal go in and output the derivative of the signal or the integral of the signal. And we will talk about that in a couple weeks, about how those are made. You can make curve shapers, which basically means you might put in a sine wave and get out a square wave, or a triangle wave or something like that. You can make those. You can make a current source. I don't know if someone talked to you in Circuits 1 about current sources, about how you don't go out and buy them like voltage sources. You actually kind of have to make one. But OpAmps make a great way to make a constant current source. So they're very useful for that. And they can also be used as voltage regulators, where you might have an unstable voltage, and then what you get out is a more stable voltage. So they're extremely useful in many, many, many different applications. And we start here rather than with small discrete components, just because it gives you a better sense of how amplifier systems work in general. So the op-amp has two inputs. One is called the inverting input and one is called the non-inverting input. They're marked by a minus and a plus, and most but not all of the time the minus is on top when it's drawn. Occasionally it's not, so do pay attention. I think there's one lab in which one of the circuits has it flipped over out of necessity, so do pay attention to that, because if you happen to mix those two up, you will get a completely different circuit than what you wanted. So you do have to kind of pay attention. Pin 2 is always the inverting input. Pin 3 is always the non-inverting input. And then pin 6 is always the output. So that's going to be standard depending on what you do. And then the other thing that you have to do is you have to connect power to it. And power is generally going to be DC, and it will usually in this class be plus 15 volts, minus 15 volts. And those go into pins 7 and 4, always. The plus goes into 7, minus goes into 4. If those pins 7 and 4s aren't connected to DC, then it just won't do anything. It's quite not useful if that happens. So we usually use, the DC is usually supplied by the same power supply, but one important thing, the op-amp circuit, when you start building circuits with it, are automatically grounded by the power supply. So you don't necessarily have to connect a ground to it. You will connect a ground if you have an input that has to be at 0 volts. Or if you're putting in a circuit that requires an outside circuit and requires a ground. But to operate, it doesn't have to be connected to ground anywhere because it's already connected to ground inside the circuit. So that is basically how they will work in general. Now, I'm going to say this more than once, this particular idea. I'm going to say this actually 2 different times, depending on what the day it is. Op-amps, we can use them by themselves, can connect some voltage to each terminal and get an output, but those circuits are usually unstable, meaning that they don't give you a nice, stable, amplified input or output. They are actually useful for some things, but not for anything we're going to do in here. So most op-amp circuits have some kind of feedback. There's 2 kinds you can use. One would be connecting the output to the inverting terminal. You can connect it actually just with a wire or through a component. That's called negative feedback. You can also actually connect to the non-inverting input and have positive feedback. Positive feedback is a whole different ballgame than negative feedback. So they will give you entirely different results. And again, we'll talk about it later. This is just a general overview. But negative feedback is good because it actually reduces distortion and instability. And for a linear circuit, if you want to amplify something, you actually do have to have some kind of connection back to the negative terminal. If you use positive feedback, generally you have to have negative feedback also. And in this class, we don't study so much circuits that have positive feedback. All circuits we use will have negative feedback when we get to that point. And the nice thing about op-amp circuits is, in general, they'll all kind of look the same. So once you get kind of a basic understanding of the basis around which we're building circuits, they're all going to look really, really similar depending on what we do. So basically, this is an example of a circuit connected to an op-amp that has negative feedback. So from the output to the negative input, there is a resistor, and then there happens to be a resistor between that negative input and a voltage source. And then the other terminal is grounded, not because it has to be, but because the circuit design needs that. So the circuit design requires a ground at the positive to make the kind of circuit we want, but it is also grounded on the inside. There are certain characteristics of ideal op-amps, which is kind of what we're going to talk about this week, is ideal op-amps. The cool thing about op-amps is they are actually really close to ideal, which means if you make calculations with them, what you actually get will be super, super, super close to what you thought you were going to get. And this is not true of like discrete transistor amplifiers. So what are the characteristics of an ideal op-amp? First of all, yeah, we have the positive and negative. So we'll get rid of that. And the resistance looking into either terminal is infinite, which means that no current actually flows into either input in the ideal case, which already is weird. Also, because of that, the voltage at the negative terminal and the voltage at the positive terminal will be equal. And again, that's one of these consistent problems or things about ideal op-amps that will occur. And again, if the circuit is set up correctly, this will actually happen. So even with a non-ideal op-amp, this will actually be really, really, really close depending on how you connect the circuit. So those two voltages, V at the negative terminal and V at the positive terminal, are treated as the same voltage node, which can set up some odd things when we do circuit analysis, but as long as you bear that in mind, it's not so difficult. The other thing that happens is at the output, the resistance looking into the output terminal is 0, which seems kind of weird. But basically it means that if you add a load resistor at the output, the voltage of the output doesn't change. So it doesn't load down the value at all. It just adjusts the current value properly and provides a voltage that will not change. That's why these can be used as a voltage regulator. So your output voltage, if you connect a load resistor between the output voltage and ground, doesn't matter what resistor you connect to it, unless you completely short it, then you would destroy it. So you can't connect a wire from the output to ground, but you can connect a resistor and it will give you the voltage that it's supposed to and it won't change. And so the current in the load resistor is just found using Ohm's law. There's not any weird loading you have to worry about. It's just simply whatever the output is and just divide by RL, and that will give you the current in that part. So for circuit analysis purposes, that makes it a lot easier because you don't have to worry about this resistor here might be in parallel and having to worry about that. And we do have to worry about those with discrete amplifiers. We don't have to worry about that with op-amps. A third ideal characteristic is that, I didn't show you that, sorry. Again, I'm looking at the finished slide. I don't remember what comes up. But the third thing is, in an ideal op-amp, all frequencies can be processed without distortion. And that won't matter to you in here because you don't have to worry about the frequency characteristics at odd frequencies. We're going to use really standard middle of the road frequencies that will be processed fine. That won't be an issue, but at the same time, it's good to know in an ideal op amp that you can process all signal frequencies. So these are the three things that you need to remember when analyzing circuits with op amps. And then I'm going to go on and talk about models. First of all, no current flowing in either input terminal. V minus equals V plus, and the current in a resistive load added is just going to be V out over RL. Those are the three circuit analysis things you'll need to remember when we start talking about circuits next week. These don't as much apply when we talk about the models of the op amps, which is the next thing we're going to talk about. So this is what you use when you are actually analyzing a circuit with an op amp and resistors around it and stuff. You use these rules. The other thing we're going to talk about is sort of how they model op amps and different ways of modeling them. So that's going to be, they are somewhat ideal, but we have to talk about exactly kind of how they get to that point.